coming to the molecular orbital diagram. Alright. So it is the energy level diagram for filling up the molecular orbitals, or we can say the MOT diagram. Now here one thing you have to remember it. Already I have discussed with you that the molecular orbital in which the electrons we are going to fill it up. It will be filled up in the increasing order of energy. That is according to Aufbau's principle, 1s, 2s, 2p in this order. Alright. Next, it will be in accordance with the Hund's rule of maximum multiplicity. Means if the degenerate orbitals will be there, then it will be filled according to the Hund's rule. That is, one electron will go to 2px, then second 2py, then third 2pz. If at all any electron is left, then the pairing will be done. Got it? It is in that particular way. It will be done according to Pauli's exclusion principle. That is, an orbital can have maximum of 2 electrons. Alright, any orbital, whether it's atomic orbital or molecular orbital, maximum it will have 2 electrons, and 2 atomic orbitals combines to form a molecular, that is 2 molecular orbitals. One is bonding, another is anti-bonding. Always bonding will be lower, anti-bonding higher. Alright, bonding is denoted by what you can say sigma, pi, delta in this way, and anti-bonding is sigma star, pi star, delta star. In this manner it will be denoted. Alright, and always it will be filled from below in the increasing order of energy. Mind it. This is not increasing, this is decreasing, this is increasing. So whenever you are going to draw the diagram, listen children, whenever you are going to draw the diagram in your notebook, you will be drawing it from below. Learn a correct habit, correct manner of drawing it. Don't draw it from in this manner. Always draw it from below. You will see now I will be drawing it. Got it? Listen carefully this thing. So draw it always from below. Got it? Now see how I am doing it. Let us say this is the first one. Now this one you can draw a circle, or you can have a square also, or rectangle as you wish. So let me draw a little bit above here. This is what you can say 1s, this is 1s. In general, this I am saying, in general. I am not drawing for any particular atom. This one, this is 1s. This is, you can say, this is your sigma 1s. This is sigma star 1s. Got it? Clear. Now next is your sigma, that is 2s. I don't have the space for, I am drawing it smaller. So 2s, so this is sigma 2s. This is your sigma star 2s. Got it? Then after what you can say 2s, 1s, 2s, then what you have? 2p. Got it? You have got 2p. Clear? So how will you draw it? That is nothing but 2p. So this is 1s, 2s, you have drawn it. Now here you will be having the 2p. You will be having it here. That is. So what I am doing is that, I am drawing it in this side, this particular side. But it will be in this order. Mind it. It will be in this order. Otherwise, let me draw it once again. It will be better. Smaller, let me draw it and draw it once again, so that I will have the space for drawing it. So in your notebook you are having enough space that you can do it. But my board is small here, so hence I don't have the space here. This is 1s, sigma 1s, this is sigma star 1s, you can see. Now we will have here this is 2s, sigma 2s, this is 2s, this is sigma star 2s. Now see here, 1s, this is, let us say, one particular atom, this is another atom of the same molecule. It can be like nitrogen, like it can be hydrogen, it can be fluorine, or chlorine. This is one chlorine atom, other chlorine atom. Alright? Any oxygen, anything it is. So 1s, because definitely 2 atoms will combine to form a molecule. Na? So this is your sigma 1s, then sigma star 1s, then sigma 2s, then sigma star 2s. Now next is your nothing but 2p. Now here I need to have some space. Got it? So one is your 2px, 2py and 2pz. We can say that. Here also same thing, we will be having 2px, 2py and 2pz. 2px, 2py and 2pz. It can be 2px, 2py, 2pz. This also it can be, no problem. There is no harm. Got it? Clear? Either 2px, 2py, 2pz or 2px, 2py, 2pz. Here also same thing. So in your book you will find it is written 2px, 2py, 2pz. What is the problem? Anything, both are same. They are in the same level. So now it is important here. Now you should listen to me here. Very carefully you should listen to me. If it is lithium, beryllium, boron, carbon, got it? Then nitrogen, this much. We can say that. Clear? Leaving behind oxygen, fluorine and neon. Any other molecule is there. Leaving behind oxygen, fluorine and neon. What I am saying? Leaving behind this molecule. Oxygen, fluorine and neon. Neon you will say it forms a molecule. That only will show it that it does not form a molecule. That only will show it by the molecular orbital diagram that it does not form a molecule. The one it forms a molecule, that also we can show, and the one which does not form a molecule, that also we can show. So we will show it here, don't worry, we will show it here that neon does not form a molecule. How? I will tell you, don't worry. So in this way, leaving behind these three only, alright, that is filling up of molecular orbitals is different. Different is what? In case of, alright, this leaving behind these three, in case of let us say nitrogen, let us say. So how it will be filled up? It will be filled up in this particular manner. First we will have here, that is 2px, 2py, alright, this is pi 2px, and this one is your pi 2py. This is your pi 2px, this is pi 2py, this is your sigma 2pz. Alright, it will be filled. Alright, it will not be for, this is not for, this is the diagram which I am doing it, it's not for oxygen, fluorine and neon. Leaving behind, I have said you already, very clearly. Alright, now next is pi 2px, pi 2py, then sigma 2pz. Then after that you will be having pi star 2px, pi star 2py, and this is your sigma star 2pz. This is your pi star 2px, this is your pi star 2py, this is your sigma star 2pz. Alright, in this way it will be filled up. For oxygen, for any other molecule leaving behind oxygen, fluorine and neon. Alright, it will be filled up in this particular manner. You see, that is, the difference will be here. This two, the difference will be here. In case of nitrogen molecule, lithium molecule, beryllium molecule, carbon molecule, leaving behind, again I am saying, leaving behind oxygen, fluorine and neon, the filling up will be taking place in this way. First pi 2px, pi 2py, sigma 2pz, then pi star 2px, pi star 2py, sigma star 2pz. See, these two are degenerate. Yeah, these two are degenerate. They lie in the same energy level. Alright, and sigma 2pz is having higher energy level. Now you will say from where we got it. That is what I said, according to Aufbau's principle. That is from the Aufbau's principle we came to know that it will be filled in the increasing order of energy. You will say in the Aufbau's principle, there is 2p lie in the same energy level. Yes, correct. But in the case of molecular orbital theory, we see that this 2 is having lower energy level. Listen carefully. This 2 is having pi 2px and pi 2py. They lie in the same energy level. They lie in the same energy level and they form pi bond. But sigma 2pz, they lie slightly higher energy level. Alright, hence they have got higher, what you can say, that is their position is higher in this particular molecular orbital diagram. This is point number 1. The reason is, alright, that is this 2 energy level is same, pi 2px and pi 2py, and sigma 2pz energy level is slightly higher than pi 2px and pi 2py. So it is being filled above sigma, what you can say, pi 2px and pi 2py. It is filled above. Alright, above that, because always we fill it in the increasing order of energy. This is reason number 1. Reason number 2, listen carefully. Reason number 2 is the difference between the sigma 2s and sigma 2pz. The difference between what? Energy. The difference between the energy of sigma 2s and sigma 2pz is quite small. It's quite small. In case of lithium, beryllium, boron, carbon, nitrogen, we can say that. All other molecules except this. Except these three. The difference between this and this is quite small. So when they will come closer, this and this, when they will come closer, they will have a chance of interaction with one another. They will have a chance of mixing. They can mix with one another because the difference between the energy is very small. Alright. So hence, to prevent that, that they should not combine, they should not interact, pi to px and pi to py comes in between sigma to p z and sigma to s. To prevent that, as the difference in energy is quite less, to prevent that, pi to px, pi to py comes in between sigma to s and sigma to pz. To prevent that, so that they cannot mix with one another, they cannot interact with one another. Got it? Clear? So for that particular reason, what you find is that is pi to px and pi to py is being filled first, then sigma to pz. But this is opposite in case of oxygen, fluorine and neon. Opposite means, what you find is that in case of oxygen, fluorine and neon, what you find is that the diagram is this way. The diagram is this. Up to this much, no problem. Beyond this also no problem. What you find is here that first we will fill this one. This one means sigma to p z. Then we will fill pi to p x and pi to p y. Alright, in case of which molecule now? Now I am saying you about oxygen, fluorine and neon. For this molecule I am saying that one, this particular one. First sigma to pz will be filled, then pi to px and pi to py. In case of oxygen, fluorine and neon, it is being filled in this way. Why? Because first reason is that is in case of oxygen, fluorine and neon, the energy of sigma to pz is less compared to pi to px and pi to py. It is less, this is less, and I have said you it is being filled in the increasing order of energy. So this is less, so first I have to fill this, then I will be filling this one. That's the first reason. Second reason is that the difference in energy between sigma to s and sigma to pz is quite large. They are, what I said, small, so they can interact with one another. Here the difference between the sigma to s and sigma to pz, the energy difference is quite large. As the difference is quite large, this is exceptional, mind it, this is large. For that particular reason, sigma to pz comes first, then pi to px and pi to py. In the previous case I said it was small. So to prevent the interactions, this was being coming first, then this. But here the difference is quite large, the difference is quite large. So there is no chance of an interaction. There is no chance of interaction between sigma to s and sigma to pz. So fair. So hence, for that particular reason, sigma to pz is filled first compared to pi to px and pi to py. Got it? So this you need to remember, and this is the difference between the molecular orbital diagram, general molecular orbital diagram for oxygen, fluorine and neon, and any other molecule we can start. Clear? Now, next is after this filling up, we will fill up now this particular electron. We will see. Let us take the example of which molecule we will take. Let us take the example of fluorine molecule. Fluorine. Let us take. So I will write it here F. Here I will write it in the middle, it is F2, and here also I will write it as F. Now if you want, you can draw a straight line also in this way, and you can put it. It's up to you, those all things. There is no harm. Now, so fluorine, what is I can say, electronic configuration? Atomic number is 9. So 1s2, 2s2, 2px, 2py, 2pz. You know that. So 4, and here it is 5. So 2px2, 2py2 and 2pz1. Is that right? 2 to 4 to 6 to 8, 1, 9. See here, 2px, 2py, 2pz. I am having less space so you can understand it. So 2px2, 2py2 and 2pz1. So we will be filling it up in this way. Now listen, see here, carefully look at the board. So 1 is 2, see here, 1 is 2. One fluorine is 1 is 2, another fluorine is also 1 is 2. So how will you fill it up? Sigma, total 4 electrons are there, 1, 2. So here first 2 electrons will go, then here first bonding, then anti-bonding. Sigma 1 is 2, sigma star 1 is 2. Here also 1 is 2, 1 is 2. Look carefully. Alright, so 1 is 2, 1 is 2. The first one, I have done it. Now, so hence 2 electron will come here, one from bonding, another one from this atom, another from this atom. Then one electron comes here, another electron comes here. Got it? Done. Next is 2s2. 2s2. Alright, so 2s2 means 2 electrons. See, here also sigma 2s2 and sigma star 2s2. You got total 3, count it in this way, that's the easiest manner. Here 2 plus 2, 4 electron, here also it should be 4. So how it will be 4? First this will be filled, then this one. Suppose it would have been 3, then here 2, then here 1. Suppose is here it will be 1. In the last AB I have said it. Suppose here it is 2. 2 electrons are there. Let us say 2. Let us say 2 is there. Then how will I fill it up? I will fill it up this one. This will be 0. 2 electron comes here. Got it? Suppose here it is 2. 2 electron is there. Let us say this is 1 electron, you can say this is 1 electron. Let us say it is there. Then this one will be 0. Here nothing will be there because 1 electron comes here, 1 electron comes here. So here anti-bonding will be 0. Finished? Okay? So in this way it will be done. Filling up will be done. But here it is what? 2s2. So here 2s2, here also 2s2. Got it? See here? 2s2, here also 2s2. So 2 electrons comes here and 2 electron comes here. Total 4. So it is done. Clear? Now, next, what is that? 2px2, 2py2, 2pz1. So 2, 2 and 1. Here also same thing. 2px2, 2py2, 2pz1. So 2, 2 and here 1. Now how will you fill it up? Total how many? Count it here. 5 plus 5, 10. So first 2 electron will come here. Then 1 here, 1 here. See the filling how I am doing it. Degenerate. First 1 here, 1 here. It's not that 2, 2 I will do it here. No. First 2 electron is being done. So 2pz2 over. Then after that 1 electron here, 1 electron here. According to what is that? Hund's rule of maximum multiplicity. 1 electron here, 1 electron here. Then after that we are having enough electron, so we can fill it up. Alright, so it is done. So how many electrons we got it? 2 plus 2, 4, 4 plus 2, 6. Total how many it is there? 5 plus 5, 10. Now next is 1 here, 1 here. Alright, another here, another here. So how many it is? 2 plus 2, 4, 4 plus 2, 6, 6 plus 2, 8, 8 plus 2, 10. Done. So it will be 2 and here it will be 2. You can see it. Now this will be vacant. Clear? Because count it and see, total here 10, the total 5 and 5, 10. Here first this I have filled it up, it is 2. Then I have taken 1 here, 1 here, 3, 4, then 5, 6, done, this level is over. Then after that 7, 8, you see my finger, 7, 8 and also my number. Then 9, 10, it is being done in this way. Then I have written the numbers here also. Got it? So this is how we need to do the filling in the molecular orbital diagram. Now I have to write the electronic configuration. Now this is electronic configuration of the atom. Now I have to write the electronic configuration of the molecule. What I will do? Just I will see it and write. Simply I will see the middle one and I will write it down. I will see the middle one. How will I do? See it. Look here. So for the fluorine molecule, I am writing it. Sigma 1s2, then sigma star 1s2. See it. Sigma 1s2, sigma star 2s2. Then sigma 2s2, sigma star 2s2. So you need to write in one line. Understood? I don't have the space there, so I am writing it. You need to write in one line. Straight. We can say that. So sigma 2s2, sigma star 2s2. In this order only. Then sigma 2pz2. See, sigma 2pz2. Then pi 2px2 is equal to pi 2py2. Either you can write in this way. Why is equal to? Because they lie in the same energy level. Either you can write in this way. Or you can write in this way. Look here. Pi 2px, pi 2py. You can write in this way also. You can write in this way also. This means they lie in the same energy level. It means they lie in the same energy level. Either you can write in this way is equal to sign, or you can write in this way. It's up to you. Got it? Then pi 2px2 is equal to pi 2py2. Then what is that? Pi star 2px2 is equal to pi star 2py2. After this. Now this is vacant. I leave it. I will not write anything. Simple over. So this is for the molecule. I got it. This is the electronic configuration for the molecule. Is equal to understood. Why? Because they lie in the same energy level. Degenerate. Got it? So this is the electronic configuration of the molecule. Just look it and write it down. Finished. Now after this, what we can come to know? See, after finding it out, this particular one, what more we can come to know? So the more we can calculate is that we can come to know about the bond order. Bond order. Bond order is what? Nb minus Na whole divided by 2. What is Nb? Number of bonding. What is Na? Number of anti-bonding. Alright, Nb is number of bonding and Na is number of anti-bonding. We can say that. Bonding means the one which is not having any star. This is bonding, this is bonding, this is bonding. The one which does not have any star. And anti-bonding is that which is having star. This is anti-bonding, this is anti-bonding. So we have to count it the number of electrons. Count it, see. 2, then 2, 4, then to 6, then to 8, then to 10. See, all these are bonding. Count it. 2 plus 2, 4, to 6, to 8, to 10. Antibonding is the one which is having star. 2 plus 2, 4, then plus 2, 6, plus 2, 8. So 10 minus 8 by 2. So it is what? 2 by 2 is 1. And it has to be 1. Why? Because fluorine and fluorine, between two fluorine atoms, what we have? Single bond. One bond only, isn't it? This is fluorine and fluorine. We have got single bond. So bond is 1. One bond. So hence bond order also will be 1. So bond order is equal to the, what you can say, number of bonds in a molecule. Oxygen will have, you can see, 2. Bond order is 2. Nitrogen will have bond order as 3. Neon will have bond order as 0. I said no, we can show it also that it does not exist. So if the bond order is 0, then it is what? It does not exist. What it does not exist? The molecule does not exist, because bond does not exist. So bond does not exist means the molecule does not exist. So in case of Ne2, in case of He2, in case of Ar2, the bond order will be 0, because number of bonding is equal to number of anti-bonding. Alright, number of bonding, you can draw it and see it. Clear? Number of bonding is equal to number of anti-bonding. So hence what we can conclude here, listen carefully. If Nb is greater than Na, Nb greater than Na, you can write it down also. Nb greater than Na, point number 1. Then bond order will be positive and the molecule exists. If Nb greater than Na, see here, Nb is greater than Na, 10 is greater than 8. Then the bond order is positive. The molecule exists. If Nb is less than Na, which is hypothetical, not possible. If Nb is less than Na, let us say, theoretically it comes, let us say, that Nb is less than, you can ask me also, sir, if Nb is less than Na, that is hypothetical, we can say that. If Nb is less than Na, then bond order is what? Negative, and it does not exist. For that reason I said it is hypothetical, it does not exist. Even Nb is equal to Na, then also, what you can say, the molecule does not exist. Why? Because in case of Nb is equal to Na, the anti-bonding, what you can say, molecular orbital, got it, is greater, is having greater influence upon the bonding molecular orbital. Hence, that also does not exist. Got it? Again I say that the anti-bonding influence of electrons in the anti-bonding molecular orbital is greater than the influence of the electrons in the bonding molecular orbitals. Then the influence of the electrons in bonding molecular orbitals. So hence, even if Nb is equal to Na, the molecule does not exist, because again and again I say anti-bonding influence is greater than the bonding. Alright, clear? So hence, what we find is that the molecule is unstable. So molecule will be stable. When it will be stable? When Nb is greater than Na. If Nb is less than Na, not possible. If Nb is equal to Na, then also it is not possible. The molecule is unstable in nature, we can say that. So this we can learn it from the, what you can say, the stability of the molecule, we can say after writing the electronic configuration, after calculating the bond order, we can say this. Clear? I hope you understood. Now next is, bond order is inversely proportional to bond length. Inversely. Bond order is inversely proportional to bond length. We can say that. Bond length. If higher is the bond order, smaller is the bond length. Alright? Like suppose bond order is 1 and bond order is 2. So when the bond order is 2, the bond length is smaller. Definitely. Oxygen will have 2 bonds. So it will be a smaller bond compared to fluorine. Again, nitrogen has bond order 3. The bond length is still smaller compared to oxygen and fluorine. Compared to oxygen and fluorine. So higher is the bond order, smaller is the bond length. Bond order is inversely proportional to bond length. But bond order is directly proportional to bond dissociation energy. Bond order is directly proportional to bond dissociation energy. Suppose if a molecule is having 1 bond and if a molecule is having 2 bonds, in which case you would require more energy to break the bond? Definitely 2. More energy. Suppose this is 1 bond, this is 2 bonds. So more energy is required to break this, 2 bonds. More energy is required. Suppose 1 more if I take it. 1 more, 3 is there. So it will require more energy. So higher is the bond order, more is the bond dissociation energy. More energy will be required to break the bond. Understood? So in this way, higher is the bond order, more is the bond dissociation energy. So bond order is directly proportional to bond energy. But bond order is inversely proportional to bond length, we can say that. Clear? So in this way, one thing you remember it, that covalent bond and the bond order, what is the relationship? Bond order can be fractional. You will see when you do it, you can see it is fractional. But covalent bond is integral. It is integers. It cannot be fractional. It means it is always whole number, we can say that, I should say. 1, 2, 3, 4 in this way. Alright? The number of covalent bonds in a molecule is always integral. It is always a whole number. but bond order can be fractional. It is not necessary that bond order will be always 1, 2, 3, 4. It can be fractional also. You will do the molecular orbital diagram, got it, and you will find it out. You will see in different molecules it can be fractional also. In this way you can say that. So hence, that is bond length is inversely proportional to bond order, we can say that. Clear? We come to know about these things. Now one more thing, magnetic nature. So here the outermost, what you can say, orbital is fully filled. So it is diamagnetic. Outermost only we are concerned of, because always innermost will be fully filled. No need to see the innermost. So see whether the outermost is fully filled or not. You have to see the outermost orbital or outermost subshell or outermost shell. So here we can see the orbital. The outermost is fully filled. See, it is paired. All are paired. We can say that. If at all, if anyone is unpaired, so now suppose it is unpaired. If it is one unpaired, then it is said to be paramagnetic. But if all are paired, as you can see it here, all are paired, it is what? Diamagnetic. So fluorine molecule is diamagnetic in nature. Suppose if it is having one unpaired electron in the outermost orbital, at least one unpaired, listen carefully, then it is said to be paramagnetic. And magnetic moment is calculated by using this formula, magnetic moment. That is what I said, magnetic moment is calculated by using the formula, that is root over of n into n plus 2. Root over of, this is root over of n into n plus 2 bm. Bm means Bohr's magneton, that is a unit. Bohr's magneton, root over of n into n plus 2, that is Bm. Bm stands for Bohr's magneton, that is a unit. This is a magnetic moment. N stands for what? Number of unpaired electrons. Number of unpaired electrons, N stands for. By this we can calculate the magnetic moment. Means, if suppose we find it is paramagnetic. Suppose if 2 to 3 molecules are there or species are given paramagnetic, which is having higher magnetic moment. How can you calculate? By this you can calculate, depending upon the number of unpaired electrons. N stands for the number of unpaired electrons. Understood? Suppose we are having 2 to 3 molecules or 2 to 3 species are given, which is paramagnetic. All have unpaired electrons. But if I ask which is more paramagnetic, so what you will do? How will you find it out? Which is more paramagnetic? We will find it from the magnetic moment. Alright? By using this formula, root over of n into n plus 2. In this way, these are the informations we get it from the molecular orbital diagram. So many things we can select. We come to know about the electronic configuration, we come to know bond order, we come to know stability, we come to know bond dissociation energy, we come to know bond length, we come to know magnetic nature. Alright? Whether the molecule will exist, not exist, everything we can come to know from the molecular orbital theory. Thank you.